session, as most of the students asked me to provide for a lecture series. So let's start with some certain basics about the voltage polarities and the current directions. And in today's lecture, we'll be essentially studying the concept of node and supernode. Before moving to these concept of node and supernode, so let's understand what is some current directions and voltage polarities. How do we set the current directions and voltage polarities? Most of the students, so prior to knowing, there are two types of current directions and voltage polarities. So one type of convention that we are using would be active sign convention. So these active sign convention, as the name suggests, is used with the energy storage elements like batteries, okay, flashlights. Those are the elements, flashlights, those are the elements that essentially release energy. These elements release energy, so they have their own energy inside, or it is stored in chemical form or electrical form. So these, when you are going for the active source, so what happens is, in case of an active source, when you are seeing the voltage and the current, suppose for an active source, if I flows in the direction, that is, your current flows in the direction of increasing potential, that is rise in potential, as is the case with the battery, then this type of power is getting released. So if I draw an element over here, this is an element, it can be a resistor, inductor, or a capacitor, okay. So it has a voltage polarity like this is its voltage polarity. Now what I suggest is my current I, that it flows like this, current I. So it is entering via negative terminal, and its exit is via positive terminal, exit via, this is negative, this is positive terminal. So one most important thing here you have to see, negative means lower potential, okay, and as far as your positive is, this means higher potential. So you have to remember one thing, there is only a potential difference between those 2 points. Suppose a battery is having 3 volts, this is plus, this is minus, this is having 3 volts, that does not mean this is 0, this is 3, this is wrong, okay. That what it means is the potential difference between these 2 points is 3. It can be 9 over here, 6 over here. So this potential difference, 9 minus 6 is equal to 3, it can be anything. It can be 10 over here and 7 over here. So this potential difference across these 2 points gives you, and wherein 10 is the higher potential and 7 is your lower potential. So this was one example. What you have to understand, there is nothing called as the zero potential or something like that. So you have to understand practically what happens in case of a battery or other elements that we are using. So now the second thing is that this type of convention, wherein your current flows in the direction of rise in potential, is called as active sign convention, okay. Current flows in direction of what, direction of rise in potential is active sign. Now if the current goes in the direction of fall of potential, suppose you have this element over here, this is x, okay, this is my v, this is my minus, this is my plus. Now suppose my current is flowing in the otherwise direction, that is my current is like this. So this would be termed like current is flowing in fall of potential, because this is the higher point, okay, this is the lower point. So this type of convention where current flows in direction of fall in potential, fall in potential is known as basically the passive sign convention, known as passive sign convention. So this convention we have to keep in mind. Suppose this is our convention, it's fall in potential, this we will take positive, okay. And if the current is vice versa like this, if the current is vice versa in the other direction. So here I marked the current with red, so I'll mark with a different color over here, green. If the current was like this, then we will take it as negative. Okay, so this you have to keep in mind. So whenever I am going to solve my nodal analysis problem, so we will encounter only, we have to take into consideration one thing, that we will take passive sign convention. Okay, so even if after taking passive sign convention arbitrary, we will take passive sign convention. So there would be no, like for example, we will not get any doubt. Essentially, if you have a battery source here 9 volt, okay, and there is a resistor over here, one more resistor over here. Now you tell me, there are two, this is bulb 1, okay, this is bulb 2, okay, this is 9 volt, okay. With 9 volt there's some current flowing over here, I, since it's in series, same current I will flow over here. So this has some resistance, this has 4 resistance. So 9 volt will be getting divided into bulb 1, for example it has 5I, okay, that would be the plus 4I. So you can get the value of I as equal to 1 amp I if you take common. So the primary important thing what you have to understand is, how could I write this? See, basically this is minus plus, if I take this direction, so this is voltage rise. Whenever you have any doubt like which, so you mark it as plus minus, plus minus. So remember, everything, whenever you are connecting a battery to a resistor or any element, it always would be a fall. Okay, because whenever you are so fall, so across the bulb it would be fall. If you have a battery that's an active source, always it would be a rise, v rise. So we know that according to the KCL, v rise is equal to v fall. Same thing I have written, or algebraic sum of v rise. Okay, algebraic sum if you want to do, or v rise minus v fall here would be equal to 0. That's it. So don't get too much stressed out. Now let's go to the nodal analysis technique, and let's understand what essentially nodal analysis is and how do we apply nodal analysis. Okay, so this is important. So many of you get confused with the nodal analysis. So prior to going to the nodal analysis, let's understand what a node and how it looks like. So suppose if I have an element like this, I'm sorry, so suppose if I have a element for a nodal analysis circuit, I have an element like this. This is my x1, okay, then this is my x2, let this be my x3, okay, and this is my x4, and this be my x5. So x5 is any element r, l and c, like previously we saw, and let this be my x6. So in order to apply to the nodal analysis here, so we have to understand what a node is. First of all, if any problem like this is given, the number one step you have to do is that you have to label it. So if I label a point over here, see, suppose I label this a, until and unless there is no any element x1, x2 or x3, it will remain a till here. So I know my a point is still here. Now I should move in one direction. See, whenever you are solving a circuit, the basic mistake the students are doing, they are moving in random directions. They will do like this, then go like this. Whenever you solve, move in one direction, or a direction. That means even if you have to complete, so one an idea in a laboratory, if you have to give a connection, so what, how do you give? First connect, the elements in series, the elements in series. Suppose this is a battery source over here, x1 is a battery source over here. Now I have to connect. So what I do is that this is a battery source x1, okay, let it be. So you, for your understanding, don't get confused. So I'll rub, suppose this x1 is a battery source, okay, it's a battery inside it. Suppose it's a battery inside it, like this, okay, it's a battery. So what I do is, first this a point I'll give to x2, okay, then I see from x2 there is a different point, this c point, okay, so I'll connect. Now this c point is getting connected till here, x4. Now this is a different point over here. See, A, sorry, B, let this be B, it will sequence, it will look good. B point. So this is a C point. Now you see over here, we have the C point, and this C point is still here. Okay. Now there's a different point over here because it's the element between D. Now you can see all the points are D. All the points are D. Suppose you go like this. So you connect all the red color like this, 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 and like this. You connect it. So now once you have given the connections, so only connections that are left are here. Hmm? One connection, see, if you then x3 and x4 is x3. Suppose x6 is also done. Okay, what you do is that in between connections are there now, this I'll mark with yellow. So these connections, yellow over here, yellow over here. Okay, this you have to give, obviously the last point, because you are moving. This you have to give, and x6. And so what will you do is x6 with x5 also you have to give, this x3 will also give. So once you have done this like yellow like this. Okay, okay, you have connected yellow like this. You have connected yellow. Only connections that are left is these connections here. These connections, once you have given all these connections, now only the x3 second part you have to give to B point. Okay, so B point either you can give to x2 or you can give to x4. Similarly here x5, this point you have to give to C point. Either you can connect it to x4 or you can connect to x6, or you can connect to the intersection between these points, because this point is C. So like that you have to do. First you have to solve in series, then you have to connect the parallel network. So you have to label the nodes. So the first point is, see, labeling the nodes A, B, C, and D. So you see there are only basically three nodes over here. One, two, three, and the this node is a datum node. Okay, then you will mark the current. Suppose this is current I1. Okay, so you see this current is getting divided here, I2. This is finally getting I3. It's getting here I4. Okay, and this current is getting divided I5. Since I have taken this as a voltage source, so I have not considered this. Okay, so this is the way how you have to do. So now when you will be solving the nodal analysis technique, so this is the prerequisites what is required for solving. So where the people are making a lot of mistake, and they are taking any sign convention. So remember, passive sign convention you have to take. That means plus and minus like this. If it is, then only you have to take this. You cannot take the active sign convention. Okay, you cannot take this. Okay, this sign convention you have to remember when you are solving the circuit. Now the nodal analysis technique, uh, if you have to apply this technique, nodal analysis technique, how to go about applying this technique. So there are certain rules, like what are the preliminary rules when you are going to apply nodal analysis. So let's understand. So how do you apply? So I will give you the steps how you will apply the nodal analysis technique. So the steps to apply, steps to apply nodal analysis, and we will be solving one problem also, so that it becomes very clear to you. So how we go about it. So the number one step that is very vital is, the first step would be to select a reference node and ground it. So first you have to select, and I will say label the nodes. Okay, select and label the nodes and ground the reference node. The reference node would be that node wherein there is no element in between. So where there is only a wire. So here you can see this is the reference node, there is no element. Suppose if there was an element in between here. Okay, suppose this was x7. So then this is D point, this would have become some E point. Now the reference node is not D, it would have been E. Okay, E. Okay, so you have to keep into mind, reference node is that node which does not has any element in between, and it's connecting more than two or three elements and grounding it. So that thing you have to keep in mind, what is the reference node. This node is also called as datum node in some books. So once you have done it, you have to label all the nodes whose voltages are unknown. So here suppose you have A, B, C. Okay, you have three nodes. So then you label all the nodes. So suppose the node suppose voltage is known of a node, so need not to label, because we definitely know the voltage across that node is this many volts. So label all the nodes, okay, whose voltages is unknown, whose voltages is unknown. So this is very important step. So you have to label all the nodes whose voltage is unknown. And and use arrows. You have to use arrows with arbitrary chosen directions to label the currents entering or leaving each node. So you have to use arrows, okay, to indicate the current entering or leaving a node. So this is very important. So this is the step number one. Let's see about the step number two. How do we go about it? Once we will be solving one problem, so it will become very easy, you will understand it. So once you have done this, then you have to apply KCL at the label node. So KCL apply KCL at the label node. This would be your step two, label node. So you have to write the currents, okay. Then once you have applied the KCL, uh, you express, okay, third step would be to express the currents in terms of voltage and resistance, okay, via Ohm's law. So this is very important step. So you have to express, first you have to write KCL, then you have to express them in terms of voltage and current via Ohm's law. Now in this step only, one important criteria that you have to remember, keep in mind, is that once you are doing so, you have to make sure your current directions and voltage polarities are correct, okay. So in order to get the current directions and voltage polarities, what you will do is choose passive sign convention. Choose passive sign convention, which I talked earlier. Passive sign convention in, that means your basically what is happening is there, when you are calculating the nodal analysis, so you have resistor, capacitor or inductor through it. So you are essentially calculating an voltage absorption, okay. So in voltage absorption, what rule is getting applied is passive sign convention, okay. So choose passive sign convention in determining, okay, determining voltage polarity and current direction. This is very important. Once you are through it, so then once you have done it, then solve the resulting set of simultaneous equations. So you can use either the Cramer's rule, or you can put directly in the calculator, okay. Solve the resulting set of simultaneous equations for the unknown node voltages. So this is very good. So as far as this is concerned, so this is how about you will go about nodal analysis. Let's analyze a problem for nodal analysis. I'll make the problem and apply these steps to you. So it will be very simple. So let's go for a problem over here. So let's take one problem. Let this be 9 volts. So this is plus minus 9 volts. So now you have to see 9 volt. This is how a problem would be given in the examination. There is a resistor, okay. There is basically, whenever you are seeing, this is the fall of potential, okay. Resistor means there would be fall, and the fall would be like this only, okay. So these polarities would not be given. So usually whenever you come across a resistor, so take this as my suggestion, okay. So there's one more resistor. This is how the problem is given. So polarities are not given over there in the examination. So you get confused, sir. Polarities are not given. So how do we take it? So that I will explain you. So here again you have this resistance over here. So and I have a current source. Okay. So this is my current source. This is 5 milliamps. Okay, this is my current source, 5 milliamps. This is my 3 kilo ohm. Okay, this is my 6 kilo ohm. Okay, this is my 4 kilo ohm. Now this is my 2 kilo ohm. Suppose I want and find node voltages. The question is find node voltages. This is the question. That's it. So how do I go about it? Now let's look back. Select a label, label the nodes and ground. See, first of all, I have to label the nodes. Suppose I label this point. Can I see here already 9 volts is given? Okay. So up, see what happens, apply KCL at label node. See, label all the nodes whose voltages is unknown. Voltages is unknown. So this node voltage is known. So no need to label it. Okay. So we will not label it because voltage is known. So label all the nodes. So if this is V1 point, okay, V1 point till here V1, I'll write with a different color for better understanding. If this is V1 point till here V1, okay. Now the other point over here would be, this is the second point. So this is V2 point over here, okay. The same V2 point will be up till here. So this V2 point remains up to here. So because there is no element in between, suppose there was another resistance in between, then this won't have been V2, it will become V3 definitely. So I know that I have two voltages. So I understood that it is asking me to find V1 and V2. Okay, so I have labeled it. And from here I have the third point. Let this be the 3 point. Okay, so I see this 3 point is moving here, here and here. So this is my reference point. So I have to ground this reference point. Okay, have to ground this reference point according to what it is given. Select and label the nodes and ground the reference node. So this I have done, but initially label all the nodes whose voltage is unknown. The arrows, now the arrows to indicate the current entering or leaving the node. So now I know for sure. So like my current that would be entering this node. So if my current I1 is entering, okay, here, so this I1 is entering V1 from this point. So current entering should leave also. So this I1 is getting divided into I2, and again this is getting divided into I3. Okay, and this I3 over here you can see is getting again divided into I4 and I5. So I5 is nothing, it is already given 5 milliamperes. So now the thing is that I have to assign it according to the passive sign convention. So passive sign convention would be plus and minus. So this is my plus and minus. So this is again my plus and minus. Okay. So wherever you see, this would be like this. Plus minus again. So this is my passive sign convention. So once I have done, I have taken my voltage polarities and my current directions according to the passive sign conventions. Now what I have to do is that, see, basically apply KCL at the labeled node. So what is the label node? 1 and 2 is labeled node. So let's apply KCL at 1. So apply KCL at V1, that is at point 1. If this is 1.1, this label node V1. So I see my current I1 is entering and I2 and I3 are leaving. So I can happily write my this thing is, my I1 would be equal to I1 would be equal to I1 would be equal to I2 plus I3. So similarly over here, if I am applying KCL at second point over here, apply KCL at V2. So what I get at V2, I3 is going inside and it is getting into I4 plus I5. I can also write I5 is equal to 2. So this is I4 plus, 5 milliamperes. 5 milliamperes. So now I1 I have to express. So if I see over here, I1 is a potential difference between these 2 points. 9. So I1 is the potential difference between these 2 points. So I can write 9 minus V1. Okay, now the step, if we go back over here, the step what it express the currents in terms of voltage and resistance via Ohm's law. So we have to express this in terms of voltage and current via Ohm's law. So I1, how can I write? I1, I can write 9 minus V1 divided by 3. Okay. What about I2? I2 can be written as here I2 V1 by, see, I2 over here V1 by 6. So I can write I2 as V1 by 6, and similarly your I3 over here, I3 is this point V1 minus V2 divided by 4. V1 minus V2 divided by 4. Now this is equation 1. Similarly over here I3, I can write I3 would be equal to what? It would be V1 minus V4 divided by 4. I4 over here would be V2 by 4, V2 by 4. Oh, sorry, this is 2 kilo ohm, not 4 kilo ohm. So it would be V2 by 2 plus 5 milliamperes. So I got this equation 1 and equation 2. Now I have to solve these equations. Once I solve these equations, I get the value of V1 and V2. So I can use my Cramer's rule, other rules, whatever I want. I can use my calculator. If I use my Cramer's rule, I'll write V1 is equal to, see, these equations first will become in terms of, if we solve the equations, this is very simple, anybody can do it. So you have to solve those two equations, you'll get this V1 minus 3V2 into 20. So you can use this Cramer's rule, 12 minus 1, 20 minus 3 divided by 3 minus 1, 1 minus 3. So you cross multiply, 12 into minus 3 would be minus 36. 12 into minus 3, then minus 20 into minus 1 divided by 3 into minus 3 minus 1 to minus 1. If you solve this, you'll get around 36 minus, you'll get around 2 volts. Okay. Similarly for V2, if you do use, you will get around minus 6 volt. But the fact that V2 is negative means that the potential at the corresponding node is lower. Okay, it is lower than the ground potential. That is it. Than the ground potential. Okay. So this is an understanding. Now let's suppose there is a case called as a supernode. Now we this was about the nodal analysis. Now we have a case called as a supernode. So what is a supernode? We have to understand. Suppose there is a voltage source between two labeled reference nodes. So if there is a voltage source between between two labeled nodes, this is called, this is or this can be generalized into a single node called as super node, and instead of solving for two different equations, two different e- two different nodes, we will solve for a single node basically. And what happens is that we solve for a single node and take the constants, see, between two nodes and get the results. Means what? Suppose there is a voltage source, suppose it's 4 volt between two labeled nodes A and B. Suppose this is our circuit, this is my resistance, this is my resistance. Okay, this one more resistance over here, this is my voltage source over here. So but in between what happens is that you see that there's a voltage source, but there's a labeled node over here. See, this node is A. Okay, this is A all. Okay, so there is this in between the two nodes. So instead of having any element, we have a voltage source. So what I do is that I'll do that, and this is 4 volt. So I know that from here, so VA minus VB would be equal to 4. So here I will take this entire node as a supernode. So this means VAB point, instead of VAB point, I'll write this as VA. Means till here, whatever my point is till here, it will become a point only. So I'll explain you with a example, and it will become much more clear. Let's take one example to understand the supernode in a better format. So basically, the nodal analysis technique, it covers what? First we have to label the node, then take a reference node, then apply KCL. Once we have applied KCL, then what we do is that we express it in terms of resistance and voltage via the Ohm's law. So these are the techniques that are involved in going for the this thing nodal analysis. Now let's go for the supernode technique and understand it in a better way. Suppose I'll write down a problem over here. This is my problem. So we'll use black. It looks good for the problem scenarios. I have a current source over here. Okay, the direction is zero point 0.5 amps. Hmm. Now I have a resistance. Hmm. I have one more resistance on top. So the value of this resistance is 2 ohms. Now the value of this resistance is around 1.5 ohms. And what I do is that I have a supernode over here. So this is my plus minus. So this is my 8 volts over here, and this you can see. Okay, so this connection over here is like this, and here I have one more resistance, and this is done. So, and this is here also, I'll say here also I have a resistance. So this is my resistance, and let this be let's suppose this is 10 ohms. Okay, now first thing what we have to do is that we have to label it. Okay, so we will label here. There is no voltage is not given, so this point is V1. Now this is a point V1 from this point is V1. Okay, we'll write with red. So if we see V1 till here, it would be because V1, and V1 is still here. Okay, now after this point there is an element connected, so we cannot write this as V1. So this has to be V2. Okay, so V2 we are seeing is still here to here. Then there is an element over here. So this point is an element over here, and so this point cannot be V2. So this point has to be V3. Okay, so V3 is this point up till here. This up till here it is V3. You can see there is no element, so this point is V3. Okay, so this point is V3, and if this point is V4, so this all the points are reference node. We can take it. This is the ground point, so this will become reference node. Now normally KCL, when we applied a KCL, so let's apply to KCL to V1. If we are applying KCL to V1, first of all I told you you will label it. Okay, so this is plus minus, plus minus, plus minus. Okay, so plus minus. So basically your passive sign convention you have to take. So your current is like this. Okay, your current is like this. So one current is going like this. If 0.5, if this is your I1, okay, then this you have to take I2 plus minus I2. Okay, whichever element is coming first, that is plus, because this is connected here, and whichever element that is coming second is minus. So here V3 is there, so plus minus. Okay, similarly here plus minus. Okay, so this would be your I1, I2, and you can write this as I3 over here. So normally if I have to apply my KCL, so I can normally write my I1 is equal to zero point 0.5 ampere. Okay, plus, tell me, I1 would be equal to 0.5 ampere. So I1 basically, I1 is getting divided into these two, this and this at node 1. So current I1 is entering at 0.1 and leaving 0.5 and I2. So I can write I1 is equal to this. And if I want to check I2, I2 would be V1 minus V2 divided by 1.5. So I2 would be V1 minus V2 divided by 1.5. So So I can normally write my I1 value is equal to zero point 0.5 ampere plus V1 minus V2 by 1.5. I1 also I can write. See, I1 is V3 minus V1 divided by 2. So those values also we can write. So this is basically here your I1 if you have to write down. So it would be I1 would be equal to V3 minus V1 divided by 2 is equal to zero point 0.5 amps plus V1 minus V2 1.5. Okay. So you have noted this. Very good. So let's suppose that I have explained you the circuit. So what happens now? Now is the concept of supernode. So I will. You have taken this down. I'll rub it over here because it would be very convenient. So we'll rub this. So what we had done essentially, we applied KCL, expressed it in terms of Ohm's law, and we got these equations over here. Okay. So let me rub it over here and let's explain. Let's let's get the real feel of the question. So the real feel of the question is that now comes the concept of supernode. Earlier I told the second node at V2 and V3. I told you previously also. I will take this V2 and V3 as a common potential. Okay, I will take it as a single node. So now if I have to apply KCL at the second node, I will consider it as a I'll consider it as a single node. In order to apply the KCL at V2 and V3, so I'll take it as a single node and applying KCL here. See, at V2, I2 is entering. Okay, so this I'll mark with yellow over here. This entire thing is one node. This point is V2 till here. If this point is V2 till here, that means I2 is entering V2. What is leaving V2? I3 is leaving V2. Okay. What else is leaving V2? See, whatever else would be leaving V3 also, na, that also is V2 only. So that means I3 is leaving V2. I4 is leaving V3. So basically, what does that mean? V2 is equal to V3. Okay. So I2 is entering, leaving I3, I4, and I1 is leaving. So if I have to write equation for the supernode, I will write applying KCL at supernode. Applying applying KCL at supernode node yields. See here. So I2 is equal to I3. Whatever leaves V2 or V3 will be supernode. I4 plus I1. So when I see this, these are the terms that are leaving. So I can go for okay. So now I know that my equations are like this. So let me write the equations again. So again I will apply it in form of KCL. Okay, I2 I know I2 is equal to V2 by V2 minus V3 by the equation, sorry, V1 minus V2 by 1 point sorry, V1 minus V2 divided by 1, V1 minus V2 divided by 1.5. So express this in terms of this Ohm's law. Okay, and I3 also I know I3 is nothing but V2 by 3. Okay, V2 by 3. I4 also I know is nothing but V3 by 10 plus V3 by 10, and I1 as usual I know it was V3 minus V1 divided by 2. So plus V3 minus V1 divided by 2. One important factor over here, see, we see this is plus minus, so we can write V3 minus V2 is equal to 8. Okay, I will say, sir, why V2? See, this is the positive terminal, so it is like positive minus negative. Okay, if it was written like this plus minus, then it would have been V2 minus V3. But in the question, it is given this side plus, so positive side minus the negative side is equal to 8. Or in other terms, I can write my V3 is equal to V2 plus 8. So I have the second constant. So I can get the second constant and put it in this equation. And if I solve these equations, elementary 10th standard, anybody can do that. So I have this values v1 minus v2 is equal to 3, 35 v1 minus 48 v2 when I substitute back is equal to 144. When I solve it, I find v1 is equal to 0 volt, v2 I'll get minus 3 volt, v3 is equal to 5 volts. So this is elementary. So one important remark over here is, see, v1 is what? V1 is voltage across current source. So that means we observe that in this particular voltage across the current source, voltage across the current source, current source is 0, is 0. So that means confirming the current source works. That means current source works with any voltage source, works with any voltage source, including 0, including 0 volts. So for now, we'll wind up this discussion. If you are liking the videos, please like, share and subscribe, and thank you very much for the love and support. So we'll wind up this session. Thanks a lot.